Do your homework. Don't mispronounce famous mathematicians' rules. L'Hopital, Euler, L'Hopital, Euler's.
Do keep track of your graphing calculator.
You find it yet?
No,
Pat, you know you can't use Mr. Levison's anymore.
I know.
Don't forget to turn your calculator to radians.
Don't forget your Taylor polynomials.
All right, here's your Taylor polynomial test. Good luck, Pat.
Thank you, Mr. Brown. All done.
Oh, really? There's another fat zero in the grade book.
Do live and die by the wheel.
Can we please get a chill day?
I think you're forgetting something, Trent.
What's that, Mr. Sheehan?
We live and die by the wheel here. And you spun for new content the whole month of May, so have fun.
Ah!
Don't walk out of the AP Calculus BC free response exam 5 minutes after the test is handed out.
You have 1 hour to complete this test.
Thank you, sir. Early lunch, boys.
Do remember to use L'Hopital's rule.
All right, Joseph, here's your test. Good luck.
Thanks, Mr. Sheehan. All right. Wait, infinity over infinity? Oh, L'Hopital's rule. Don't forget the product rule on implicit differentiation problems. Gee, when do these get so easy? Do dump before polar and parametric free response questions. Okay, Pat, here's your parametric test. Good luck.
Thank you.
So today we're looking at question 3 from the 2006 BC test. This is a parametric question and also a calculator question. So to start off, let's just read the question. An object moving along a curve in the xy plane is at position x of t, y of t at time t, where dx equals that and dy dt equals that for t is more than or equal to 0. At time t equals 2, the object is at the point 6, negative 3. So for part A, find the acceleration vector and the speed of the object at time t equals 2.
Okay, first of all, when we're doing the acceleration vector, we need to make sure that we use the proper notation, which looks like this. And now, in order to find the values that go in the x and y direction of the vector, we need to first plug in the dx dt and dy dt functions into our calculator. We'll do those in separate lines. Then we're going to take the derivative at the point that it asks us, t equals 2, which will give us the acceleration because the current functions give us velocity in those directions. So if we take the derivative of 2 at the dx dt function, we find that we get the answer 0.395. And similarly, if we do that on the dy dt function, the derivative at 2, we get the value negative 0.741. Alright, so for the next part of the question, we have to use our handy dandy speed formula. And so, first of all, we're just going to write down the speed formula. So that the speed formula is square root of dx dt squared plus dy dt squared. And so now we're going to plug in our dx dt and our dy dt at the value of t equals 2. And so when we do that, we take the square root, and we'll have x prime of 2 squared. X prime is the same as dx dt, and so we'll square that, and then we'll have y prime of 2 squared. Y prime is the same exact thing as dy dt as well. And so once we get this, we'll plug this into our calculator. And so after plugging this into our calculator, we find that our speed is 1.207.
Next we have part B, which says the curve has a vertical tangent line at one point. At what time t is the object at this point?
Okay, to find the vertical tangent line at one point, we need to think about what the vertical tangent line really means. The vertical tangent line is a slope that is undefined. It's no real value. And we know the slope to be the change in y over the change in x. And in order to get that to be an unreal value, we know that that has to correspond with the x equation. In this case, dx dt equals inverse sine of 1 minus 2e to the negative t. So we're just looking for where this equals 0. So we'll set our equation. I'm not going to write it all out. I'll just say dx dt equals 0. Now, since we have the help of our calculator, we'll plug that equation into our calculator, or we already have it in there actually from the last part, part A, and we just go to second calculate 0. We find the left bound and the right bound sides and find that it equals 0 at the point 0.693.
Now let's take a look at part C. Let m of t denote the slope of the line tangent to the curve at the point x of t and y of t. Write an expression for m of t in terms of t and use it to evaluate the limit of m of t as t approaches infinity. Alright, so for part C we need to find the slope of the tangent line to the curve at the point x of t and y of t. And for this we'll use m equals dy dt over dx dt. And we know this because this is the formula we should have memorized to find the slope for these problems. And we can write that out as 4t over 1 plus t cubed, and multiply it by 1 over inverse sine of 1 minus 2 e to the negative t, and that will give us our slope.
So since we have our slope function at this point, we need to evaluate the function as t approaches infinity. So let's write this down. The limit as t approaches infinity for the function which we have defined here as 4t over 1 plus t cubed times 1 over the inverse sine of 1 minus 2 e to the negative t. So you'll notice that this is a lot to try to put in infinity to all the t values, but if we break this up by halves, you can see that this one right here, if you plug in infinity, is going to require L'Hopital's rule, because this will be infinity over infinity, which is an indeterminate form that we should know. So if we take L'Hopital's rule, I'll write it over here, you'll end up with 4 over 3t squared, of course the limit as t approaches infinity, and we'll find that as t approaches infinity, it's going to equal 0. So since this portion equals 0, we know that 0 multiplied by anything is still going to equal 0, so we don't even need to evaluate the limit of t as it approaches infinity for this half of the function. We can call this 0. That is our answer.
Now for part D. The graph of the curve has a horizontal asymptote, y equals c. Write but do not evaluate an expression involving an improper integral that represents this value c.
Okay, we're looking for a horizontal asymptote, which is basically clearly a horizontal line that is defined by a y value consistently across the entire interval from negative infinity to infinity. So in order to find this, we first need to consider the fact that we have a defined value of y at an instant. And this instant is t equals 2. And we know this value of y at this point to be negative 3. So we know we have to include this into our integral. So we'll set that first. The next part we have to consider is how much is this value changing over the interval from the point that it was taken to infinity. So in this case, it's 2, and we're seeing how far it changes to infinity. That means that our integral's going from 2 to infinity. And we're looking for the total change, which means we should take the integral of the dy dt function. This is similar to when it asks you to find the total distance traveled of a velocity function. You would take the integral of the velocity function in order to find this. So since we don't have to actually evaluate what that is, and since this function is defined, we'll plug it in and get negative 3 plus the integral from 2 to infinity of dy dt, which is actually 4t over 1 plus t cubed dt. And that is equal to our c value, which is the value of our horizontal asymptote.